Hi, I'm Matthew Stolt. I'm from Beaverton, Oregon originally. I am currently a student at Oregon State University and recently have just finished up my second summer internship with the center. I got very interested in chemistry pretty much my senior year of high school. I had a teacher who took it upon himself to stay after class with me and my friends and give us this different view on chemistry. The idea that we always had to learn it out of a book or in a lab. He gave us this ability to just talk with someone. We'd stay after and just ask him questions, things that we were actually interested in, what was going on in almost research, what was going on in the world, how things actually worked, the more in-depth topics, and he would stay after class and just talk with us. And I originally came to Oregon State as a chemical engineer because I thought my dad being an electrical engineer for Intel for a very long time, that engineering was really something I wanted to do. I wanted to build things, but I was really interested in chemistry, and I'm really interested in small compounds, working at an atomic level, working at molecular levels, how those all work throughout the body, throughout materials, throughout anything. I realized very quickly from a couple of my friends that chemical engineering wasn't exactly what I expected, and that chemistry is really where I wanted to go, and that I really wanted to work with this whole synthesis idea. I work on creating a lead selenide titanium diselenide thin film through what we call is the modulated elemental reactance method, which is where we very simply heat metals through means of electron beam guns or through means of just heaters, and when we vaporize these, we can catch them on a silicon substrate. If we anneal them, basically just simply heat them, they'll react into these kinetically, not thermodynamically stable products. Here in the Xray diffractometry room, behind me is an instrument that I work a lot with. I spend a lot of time in this room. I work with Xray diffractometry to figure out crystal structures. This idea that in crystalline materials, things that you see all the way, salt is one that everybody sees. You know this cubic structure, that it's a cube. Well, how they figure this out is a simple geometric technique of sending in X-rays. The X-rays that scatter off, you can figure out your crystal structure, your lattice, as they say. I work with mainly crystalline materials, and these materials that I make through my vapor deposition and after heating them, I create these crystalline thin films. And the importance behind this XRD, behind this X-ray diffraction, is that I can very quickly tell myself, yes, I've made it, or no, I didn't. There's this idea behind it that the center has a lot of collaboration, and we get to work with a bunch of different people, whereas when you're stuck in one lab, you find yourself asking questions, and you don't really know where to go. I learned how to work with people a lot more. I learned how actual labs work rather than what I expected. After finishing 2 summers now working for the center, I can really say that I've definitely enjoyed it.